Yesterday, we had talked about some very basic probability problems. You're rolling a dice, flipping a coin, pulling a card from a deck, and they were getting a little bit complicated where we had the or statements. What's the probability of pulling a king or an ace card, or an ace, or what is the probability of pulling a 7 or a 6? And even though those were or statements, we could just look at the total cards that satisfy that statement in our deck. There wasn't any overlap. There wasn't a card that was a face card and an ace. There could only be that the card was an ace or a face card. Couldn't be both. But instead, what if I had asked, what's the probability of pulling a red card or an ace? Well, we have two aces that are also red, so there's some overlap there, and today we're going to learn how to account for that overlap. So here, when you consider all outcomes for either of two events, you form what is called the union of A and B. When you consider only those outcomes that are shared by both A and B, you form what is called the intersection. So the intersection is where both events overlap. So when I was talking about a red card or an ace, well, those two aces that are also red, those would be the intersection where that overlap occurs. Now, the union or intersection of two events is called a compound event. And over here we have a picture that helps represent what's going on. So we have two events, and if there is some overlap, it would look like this first picture here, the union of A and B, where we have everything that is in both Venn diagram circles. We learned about Venn diagrams many years ago, and the dots that are in the middle belong to both events. They're shared. And the intersection is just that area that belongs to both circles. Now, if the intersection is empty and there's no shared events or shared items, then it's like what we were talking about yesterday, pulling an ace or a face card. There is no overlap, so there's no intersection. It's empty. So what happens is to find the probability of A or B, you must consider the outcomes that are in the intersection of A and B. Two events are overlapping if they have one or more outcomes in common, as shown in that first diagram. And then two events are called disjoint or mutually exclusive if they have no outcomes in common, as shown in that third diagram. So when we were talking yesterday, we could just simply add, hey, there were 4 aces and 12 face cards. So we added them together and said there were 16 cards altogether out of 52. Well, we can't simply just add in this case, because if they are overlapping, if we were looking at A, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 dots in event A, and 1, 2, 3, 4, 5, 6, 7, 8 dots in letter B. So if we were just to add them together, 9 plus 8 is 17. Well, there aren't 17 dots here altogether. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 altogether. So we have to account for that overlap, and that's what we have down here. If A and B are any two events, the probability of A or B is the probability of both of them separately minus the intersection. So we would write that as the probability of A occurring plus the probability of B occurring minus the probability of A and B. So minus what is in both of them. So going back up here and looking at that, well, there are 4 items in the center. And if we were to do 9 plus 8 minus 4, that does give us 13, which is what we get when we add up or count all of the dots in this Venn diagram. So by subtracting the intersection, it gets rid of the overlap or the duplications. Now, if A and B are disjoint events like we had yesterday, then the probability of A or B is the probability of A plus the probability of B. We don't have to subtract anything because there's nothing to subtract. There's no intersection. But we always need to take the overlap into account. So on the next page, you roll a 6-sided number cube. What is the probability of rolling a 2 or a 5? Well, we can't roll a 2 or a 5 at the exact same time, so they are mutually exclusive. So let A be the event rolling a 2 and B be the event rolling a 5. A has a 1 out of 6 outcome and B has a 1 out of 6 outcome. So the probability of both of them happening is 1 over 6 plus 1 over 6, or 2 over 6, which is equal to 1/3. Now, that's just a different way of doing what we did yesterday, where we just said, okay, well, how many 2's do we have? 1. How many 5's are there? 1. So we have 2 successes divided by 6 possibilities. Now, example 2, a card is randomly selected from a standard deck of 52 cards. What is the probability that it is a face card or a spade? Now, this Venn diagram here is here to help us look at the overlap that occurs, but we want to also do this mathematically. So we see that there are 3 cards here. There are 3 cards here that are spades and face cards. So we can write it as, the probability of a spade. There are 13 spades in a deck, which is 1/4. And I'm writing both fractions because when we're adding and subtracting fractions, we need those common denominators. Now the probability of a face card, well, there are 12 face cards out of 52, which will simplify to 3 over 13. See, those reduced fractions are not going to be easy to add, so we're going to use the unreduced fractions. Now, how many do we have in the overlap? We have 3 out of 15. So the probability of a spade and a face card was 3 out of 52, which again can't be reduced. So now we can figure out, so the probability of a spade or face card is going to be 13 out of 52 plus 12 out of 52 minus 3 out of 52. And that equals 22 out of 52, which is 11 over 26. So if we were to count up these cards, there should be 22 within all these circles here. So that's why I don't want to always reduce my fractions without writing out the work, because we were able to use the unreduced fractions in our problem down here to make life a bit easier. Right, then example 3. Of 100 students surveyed, 92 owned either a car or computer. Also, 65 own cars and 82 own computers. What is the probability that a randomly selected student owns both a car and a computer? So this one we have to think about because we already know what the or part is. Of the 100 students surveyed, 92 own either a car or a computer. So we have in the formula, we have this part. We also have that 65 own cars and 82 own computers. What is the probability that a randomly selected person owns both a car and a computer? What we're trying to figure out here is this one. So the probability of getting both, 92 out of 100, is equal to the probability of a car plus the probability of a computer, which is 82 out of 100, plus the probability of A and B, or the car and the computer. So we can combine like terms. So 92 over 100 equals 65 plus 82 is 147. Oops, this should be a minus. Minus the probability of A and B. Subtract 147 over 100 from both sides. Now again, because our denominators are the same, it makes life a lot easier. 92 minus 147 is negative 55. So negative 55 over 100 equals negative probability of A and B. Well, if they're both negative, then we can multiply everything by negative 1 to make it positive. So the probability of A and B equals 55 over 100. So the probability of selecting a student that owns a car and a computer is 55 out of 100. This problem here, of 200 students honored, 30% won awards for history and 45% won awards for science. 24 students won awards for both science and history. One of the 200 students is chosen at random to be interviewed for a news station. What is the probability that the student won an award for history or science? So the first thing we need to do is convert these percentages into actual numbers. So 200 times 30%, or 0.3, that's going to be 60. So 60 students were awarded awards for history. 45% were awarded for science. So 45% of 200 is 90. And we know that 24 won for both history and science. So the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So the probability is going to be A. Well, we can call A history or science, it doesn't matter. So 60 out of 200 plus 90 out of 200, 90, not 900, minus 24 out of 200. So again, because everything has the same denominator, we can just add and subtract. So the probability would be 126 out of 200. Now, it doesn't say to make the probability as a percentage or a decimal or anything like that, but you could if you wanted to, and that would be 0.63 or 63%. So you have to be comfortable using that formula and going in either direction, figuring out the left side or something on the right side. We have 4 things in this formula. If you are given 3 of them, any 3 of them, you can figure out the fourth one. And the last thing we'll talk about is something called the complement. The complement of an event are the outcomes that we don't want. So, and it's noted with this little bar above it is a complement of A. So, for example, if the event that we were focused on was what is the probability of rolling a 5 on a dice, the complement would be, not rolling a 5 or rolling a 1, 2, 3, 4, or 6. So the notation on that is read as a bar, and to calculate the probability of the complement of A, it's 1 minus the probability of A, because probability is a number 0 from 1, and if you take the probability of something happening plus the probability of it not happening, you have to get 1. And we can use this fact to make some of the problems easier. So this one, a card is drawn from a standard 52 card deck. Find the probability of each event. The card is not a 7. So if we want to find the probability that the card is not a 7, we could do 1 minus the probability that it is a 7, because it's much easier to count up the 7s here. And some of you may do this on your own without even thinking about it. Instead of counting all these up, you might have said, well, there's 52 cards. 52 minus the 4 7s is 48. So my probability is 48 out of 52. That you're doing the same thing, just not writing it out mathematically. So 1 minus the probability of a 7 equals 1 minus 4 over 52, because there are 4 7s. Now we're going to write 1 as 52 over 52, and we get 48 over 52. Now for some problems like these, is doing this formula quicker? Maybe not, but it is an option. You can use either tool. So B, the card is not a red face card. So this one might be a little bit more difficult without using subtraction. We have 6 cards that are red face cards. So we can do 1 minus the probability of, I wrote 7 there, but we can call that red face. So 1 minus 6 out of 52, which is 52 over 52 minus 6 over 52, which is going to equal 46 over 52. And it just dawned on me that we did not reduce the fraction in the previous problem, so I will go and do that. This fraction is 23 over 26, and the other one, 48 over 52, is going to be 12 over 13. So using the complement does make things a little bit quicker in some instances. So now on the next page, we have 2 6-sided dice are rolled. There are 36 possible outcomes, and we showed them here. Find the probability of each event. And I'm going to let you try these, and you can do them any way you want. You can use the complement. You can count them up, count the sums up, whichever is easier for you. So pause the video, and then try it and unpause it, and see what we get. All right, so here are the answers. Let's talk about them real quick. For letters A and B, I used the complement because there were fewer things to count. So the probability of sum is less than 10. The complement of that would be greater than or equal to 10. And there were only 6 sums that were greater than or equal to 10. So I did 1 minus 6 over 36, and that got me 30 over 36, which reduced to 5/6. Then for letter B, the sum is not 7 or 8, so I said, okay, 1 minus the probability of the sum equaling 7 or 8. And there were 11 sums that were 7 or 8. If you look here and count, we have 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11 possible sums to get 7 or 8, so 11 out of 36. 1 minus that will get us 25 over 36 that we can't reduce. And then for letter C, though, the sum is greater than 9 or less than 4. Well, for this one, it was just easier for me to count these events separately. Less than 4, if the sum is less than 4, it's only these three. It's only those three that are less than 4. And then it says greater than 9, so 10 or more. Well, we already have those circled here in green. So I just added those two probabilities up, and there's no overlap with those events. So we didn't have to subtract anything. And then we can reduce that to get 1/4. Right, so again, it's very important that you are being careful with your formula usage and knowing the difference between and or. The intersection is where both events are true. So thanks for watching. Make sure to like the video and subscribe.